All right, it's time. Let's get started. So, welcome to the co-class for 21B. My name is James. I am the math specialist who teaches some of the co-classes along with other people like Grant and Ryan and Jen and Sarah. No, not Sarah, really so much anymore. Anyway, so we should go over the syllabus for this class as quickly as possible, and then we will get into the calculus. Feel free to ask questions. I'm happy to answer anything I can. And yeah, I think that's it. We'll go over everything. The only real important thing is that for those of you enrolled in the class, meaning you signed up using a CRN, the CRN being 55341. If you signed up that way, you have to attend. If you didn't sign up that way, you don't have to attend. That's basically it. That's like as far as I'm gonna say a bunch of stuff that's moderately maybe important, but the actual important thing is if you were enrolled in this class for one workload unit, meaning a unit that counts towards being full-time, but not towards graduation. If you're signed up that way, then you need to attend class in person so that you can pass the class and get the units. If that's not you, you never have to come, but you should come, obviously, right? You should come. Please come. I want you all to come. I like seeing faces. It makes it much easier to teach to a class of like, what, 17 people than like 3 people. So please come so that it's better for everybody. That said, let's go over the Canvas for this class. I can really, there we go, that's better. Okay, so we'll look at the syllabus. This is not really the important page, but we should look at it just to make sure everyone has seen it. Again, my name is James. You're welcome to call me James, but if you're not comfortable with that, I get it. You can call me Mr. Parmenter, which is so much more to say. So if you can call me James, it's much easier. And also, I like my name, so call me James. Lots of things. So Co-21B meets now. You're here. Great. I'm the instructor. You can reach me by email, really is the best way. If you try calling me, it's probably not going to work because we don't even have phones anymore. We have Zoom phones, which means I have to have like Zoom open on my computer, and then someone might call me on it, and I'll be like, what's going on? So just email me. It's easiest. You can also come by my office, which I'm in often, in 2244 Dutton Hall, or you can find me in my office hours, which we'll talk about later because they're kind of all over the place. Grading, as I mentioned before, if you signed up for this class with a CRN, you will get a grade, either pass or no pass. The way you pass is by attending. How many times? 70% of the time. How many classes do we meet? 20 times. 70% of 20 is 14. So you have to show up 14 or more times and like participate, be engaged, not looking at your phone or whatever. Obviously, you look at your phone sometimes and think it's totally fine, but you know what I mean? Like paying attention, saying things, responding, listening, working with each other, maybe. Also, yeah, we'll talk about the working with each other thing in a minute because there's a thing. Yeah, so your grade is purely based on attendance. If you aren't registered in the class, you're still going to see a grade in Canvas. Just ignore it. It's not important at all. Let's see. If you're enrolled in the class, yeah. If you're not enrolled in the class, meaning I added you to Canvas manually, or you filled out a Google form to get added, then you should still come, but you can also attend live via Zoom, like some people are right now. One person? 2 people. Hi, people on Zoom. For people on Zoom, here is the attendance form, which I'll point out to everyone actually in a moment here. But if you're attending in class, you just fill out the attendance form making its way around. If you're attending via Zoom or watching a video later, I would very much appreciate it if you would fill out this form. So even if you're enrolled, meaning you registered with the CRN and you can't make it to class one day, you won't get credit for attending as far as your grade is concerned, right? You have to come in person. That's something I decided on. I just feel like it's better for everybody. But if you still want to like make up the class because you want to see what happened, great. Fill out this form. It's pretty straightforward. You write your name, your email, your email first, then your student ID number, then your first name, then your last name, then which class you're attending, Co-21B, and then how you attended either live, virtually, or recording. And then importantly, the correct date, month, day, full year. Please enter the full year. It'll make my life easier later when I'm sorting through the data. The reason I need you to do this is because at the end of the quarter, I'm responsible for compiling all of the data for the students I served. And this is one of the ways I serve students. So my boss asked me to get this to her, and then I have to like go. It's kind of pain in the butt actually, but it makes it easier if you fill this thing out correctly, because I can sort it on a Google Sheet and just like copy and paste it to other places. So please do this when you attend virtually. The two of you, please fill it out right now. And I think that's it as far as that goes. Again, if you have questions, you are welcome to ask them. Let's see. Yeah, fill out the form. Yeah. As far as this class goes, it's pretty straightforward. I'm going to be showing you things. I'm going to be asking you questions. You're going to be working on math. You should come with a pen and paper, or pencil and paper, or tablet and what do you stylus, right? Whatever writing device and thing to write so that you can write things down, because that's often how people learn things. What else to say? Yeah. Oh yeah, the things about if something is impacting your success in math, please don't have this. I'm sorry, this is very distracting over. This table is like not falling apart, but this is terrible. It's really like often. Oh well, deal with it. Ow. Actually, ow. There's a hazard up here. I'm gonna cut myself. I have to be careful. Yeah, that's kind of terrible. But it's not okay. Anyway, it's fine. So about this class, if something is impacting your success in math, please don't hesitate to talk with me. I am a resource for you. I'm also bleeding just a little bit, but not too much. Okay, yeah. Feel like John Stewart over here when he cut his hand with the glass recently. It's lovely. Okay. If something is said in class by anyone, including myself, that makes you uncomfortable, please talk with me about it, or someone I work with if it's me saying things that make you uncomfortable, but it's never been an issue, so I don't anticipate that. But in case something's going on in this class or one of your other classes, don't hesitate to come talk to me or someone else about it. As far as class goes, our classes now on Tuesdays and Thursdays in this room at this time. Each class period is going to consist of me showing you stuff, you working on stuff. If there are things you'd like me to talk about, you can let me know ahead of time. That's wonderful. It makes it easier for me to know. Sorry, I'm focused on the blood here. And yeah, come to class prepared. If there's something I can do to make your learning experience better, like I've said this before, but I'll say it again. One quarter student asked me if I could write using a thicker pen, and I did because it made it easier. I was using a thinner pen point, and it was harder to read. So if there's something else you think of that would make it easier for you to understand what's going on, that'd be lovely. Yes. Thank you so much. It'd be much less distracting. I'll bandage myself up. Oh, these are cool. This is probably an appropriate size here. Yeah, I definitely should call facilities as well and see if maybe someone can fix this at some point. Thank you. Appreciate it. So as I was saying, if there's something I can do to make your learning experience better, don't hesitate to let me know. I'm happy to make accommodations, like talking more slowly, which I'm not great at, but I'll try to do, and writing things as legibly as possible, which I try to do. But also, if you have a formal accommodation through the SDC, please get that sent to me. It probably won't affect much because there's no exams in this class and everything's already being recorded, and I will post the lecture notes. So you're welcome to do whatever, and I'm happy to make accommodations in whatever way I need to, but they probably won't have much bearing on how this class works for you because everything's kind of already available in all the ways. That said, happy to make accommodations for anyone who needs them. Zoom instructions, we probably don't need to go over because we've been using Zoom forever. I should delete that next time I write a syllabus. So notes about the class. It's worth, so if you're enrolled for the one workload unit, again, that unit counts towards being full-time, but not towards graduation. That's kind of all there is to say really about it. Sure. I'm ever hopeful that someone will one day use the discussion tab to ask me a question and everyone can see the question and other people can respond. You can use the discussion tab. It's right here. And then you could like go here and write a question. You can be like, add a discussion and then ask a question about like, hey, James, what is the antiderivative of, you can even do this. You could click on the little equation thing and then write like f of x Oh, I'm doing it the weird way. Sure, no, I'll just directly do. I prefer to do it this way. F of x equal to tangent of x. For example, you could type that and post it, and then later on, not right now. Okay, fine. You could ask a question here, and then I could respond, or one of you could respond with your thoughts. It's, I guess, a little bit like Piazza, however you say that, but just for this class. So if you want to ask questions there, I will see them and I will respond to them. I won't answer this question just yet because it's not something we've covered yet. But the nice thing about this, the reason I'm pointing this out specifically is because it's a place where it's easy for me to write in typesetting that looks nice, right? I can use nice mathematical symbols and all the stuff there so that I'm not like writing like X and then like the caret to the third to right. It just looks better. So if you have a question, you can't immediately get to me. Instead of emailing me, you might ask it here, and then everyone gets to see the response as well. It's kind of nice. Yes, I will address the question about the co-class, which I will address that in a moment, Jaylene. Hopefully I'm saying your name right. Yeah, back to my cursor is way over here. Back to the canvas. You can use discussion, sure. And then as far as the class goes, like as many math classes are, the stuff you're learning is built upon the stuff you already learned. So you kind of have to make sure you keep up with stuff. If you get behind, it can be really easy to get too far behind. So I would encourage all of you to stay as up to date with the material as you are capable of. Successful students are usually spending 10 to 20 hours per week doing the homework, practice problems, and studying for Math 21B. The more you practice and ask questions, the more successful you will be. Where else can you get help? My office hours, which I'll show you where they are in just a second. And then there's also math tutoring and math drop-in, which is in the lower level of the library. That starts on Sunday, and it's open Sunday 3 to 7 and Monday through Thursday. I think I've written 10 to 5. Let's see if that's right. Here's our website. Here's the math part. Let's see. Does it say when drop-in is open? It might not say yet. Let's see. Oh, yeah. Nope, it is. So every Sunday, 3 to 7, and Monday through Thursday, 10 to 5, except for apparently there's no one to help with. Well, that doesn't matter for us. For Math 21, 3 to 7, and every Monday through Thursday, 10 to 5. So there's student tutors down there, and then occasionally I'll be down there, or Grant will be down there, or Jen, or Ryan. We'll see when I'm down there in just a minute. And then to answer the question that was asked, so someone asked, is there a way that I can drop the co-class but still be on the Canvas? Yes, there totally is. Anyone is welcome to drop the class if you are enrolled in it with the CRN, and then I can happily add you back into the Canvas. You just have to send me an email. The only difference really is that you won't get one workload unit. But if you don't need one unit to bring you up to 12 units, you don't really need to be enrolled in the class. It's kind of all there is to say about that. Questions so far? This is the exciting part. Not the exciting part. Let's go ahead and look. So the place you'll actually, which I'll change to the homepage probably by Friday, is the modules, is where actually anything useful is. And let's go ahead and look at the student view, just so you see the things that you'll actually see. So here's what you'll see currently. Useful links. Some links to the class attendance form, which I showed you already. Grant's 21B website, which, let's be honest, you all know, well, you might not know, but you will know that that's where I'm just stealing stuff from outright. Like Grant is my coworker and he writes lots of good notes. I usually try to change things a little bit so that you can also look there on your own and have examples that are unique. But yeah, that's where I'm getting all my coursework, really, all my inspiration. Let's go back to the modules. This is also a useful website, which I think this website is where Babson is getting a lot of his material from, is Kuba's 21B website. If you look over here, it has some things, some practice exams and solutions, and then it has lots of scan problems, and then just a bunch of assigned problems, and then their solutions written somewhere. I know that he has also posted the solutions. Where are the solutions here? Good question. I want to know now. Yeah, right over here. 21B homework and exam solutions. So if you're looking for more practice, this is a great place to go, I think. My website, which is not worthwhile unless you want to see a picture of my cat. And then, oh, this is actually, we'll use this. This is a visualizing the Riemann sum. When you talk about area under a curve, it's a really useful tool that lets you kind of just see how things work, but we're not quite there. And then I have the exam dates. I don't think I have Babson's on there yet, but I will eventually. Yes. Oh no, I don't have Babson's, but I do have Parlax. So I'll update that just so really it's for me actually, so that I know when your exams are. So I'd be like, I don't want to go look at the actual classes Canvas. I can just look here instead, which is easier for me. What else here? And then some useful handouts. The derivative practice handout that hopefully some of you did over the break, maybe, possibly. I did post this and write an announcement, be like, hey, if you've got time over the break, you should definitely work on this. And then solutions. So it is good practice. Yeah. And then there's some other handouts here that are useful as well. Some derivative rules, which we should be aware of. Really like just how derivatives work. Like, yes, the derivative of sine of x is cosine of x, and cosine of x is negative sine of x, and all the derivatives we learned in 21A and some other, yeah, that's kind of it. I would encourage you to review that because your knowledge of derivatives is very, very, very required, important for knowing how to find antiderivatives. You're kind of just going backwards. In fact, that's what the handout that I posted was really all about, was finding the antiderivative of some known functions. And then we have, oh yes, so Parlac, she is posting practice problems, and I looked at them and I thought they were really good, and I asked her if I could post them for the people who are not in her class. So these are the practice problems from Parlac. Do I have to download them? No. There's a lot of good questions here. I will put, when I see them on her Canvas, I will post them for you. Here she's asking you to find some antiderivatives, and then some more antiderivatives, and then some more antiderivatives, and also find the constant. We'll talk about this kind of stuff, but I just want to point out what I'm trying to say in a roundabout way is there's lots of places to get practice. There's lots of practice. You should never be at a loss for where can I get more practice? There's lots of problems to practice on. So if you're looking for practice, look in the modules. Let's see, is there anything else here? And then we have an integration flow chart, which we'll talk about later after we talk about integration methods, which actually brings me to an important point. As far as I can tell, let's look over here. Not here. Where'd you go? Sorry, over here. Apologies. 1 second. So, yeah. Oh my gosh, so many things in the way. Let's go over here. So this is Babson's 21B website. His Canvas is really just a link to his 21B website. And it kind of shows what he's going over. I've noticed a couple things. One, he's at least not talking about section 4.8, which is antiderivatives, which is where we're going to start today. Because although you don't have to start with antiderivatives, it does help to know about antiderivatives a little bit before we move into the finding the area under a curve portion of 21B. And then goes to chapter 5. And then he skips to chapter 8, which actually I think is better is not the right word. That's the way I learned it. We learned the methods of integration before we learned about the applications of integration. But the syllabus goes chapter 5, chapter 6, chapter 8, which is the way Parlac is going to do it. So after we complete chapter 5, let me ask, how many of you are in Babson's class? Okay, how many of you are in Parlac's class? I know it's everyone else, but like, okay. So majority Babson, but I feel like I can't just like, we're going to do this and not do that. So I need to think about exactly what we're going to do. We might be doing some group work at the boards so that people in Parlac's class can work on the things they're working on. People in Babson's class can work on the things they're working on. I haven't decided exactly yet, but we will try to do something so that people aren't like left out in the cold, be like, well, we're learning about integration by parts, but in this class, we're going to find volumes of revolution, right? Those are very different, although not unrelated. So yeah, here's Babson's 21B website. Anyone can find it. It's really just mostly Kuba's website, just reorganized. So he's using, which is fine. Like Kuba did a lot of good stuff when he was an instructor here and made a lot of useful material. So I don't have an issue with it. I just want to point out that you can find all this other places as well. And then That's that. All right. So, and those are the notes from Parlak's first lecture yesterday. All right. What else? I think that's everything in the modules for now. Yeah, okay. After class today, I will post the video from class, the lecture notes from class, as well as there was something else. I've forgotten what it was. It's all right. There was something else I meant to be talking about posting though, but I don't remember what it was. Oh well, it'll come back. All right. Questions, comments, observations, concerns. Nothing. Fine. Also, if you have a question later on, you're always welcome to ask it. Guess that means we can start with the math. I should move this though. So let me move this out of the way. Oh, I know what I was gonna say. Well, actually, that wasn't it, but I'm not sure if Parlak is planning on posting solutions to the practice problems she posted. If she isn't, I might find time to write them. We'll see. Oh, I know what it was. I was gonna talk about my office hours. Thank you, James. There we go. Sorry. Myself. So back up here, let's maximize that for a second. So my office hours are kind of all over the place. Really, if you're trying to find me in office hours, the easiest thing to do would be just to look at my office hours in Canvas or on my website. So here's when and where they are. They're the same times every day. They're just in different places. So my office hours are Monday, Wednesday, Friday, 1 to 4, Tuesday, Thursday, 1:30 to 2:30, and then every day except for Friday, 10 to 11. It's kind of confusing, but then they're in different places. So Monday, 10 to 11 is in CADS, which is the Center for African Diaspora Student Success. It's over in the South Silo. And then from 1 to 4 is in drop-in, which is over in the library. And then on Wednesday, same hours, 10 to 11, but then 10 to 11 is in drop-in, and 1 to 4 is in C class, which is the Center for Chicana Latinx Academic Student Success. It's over above the coffee house, right up those outside stairs there. And then Friday, no 10 to 11, but 1 to 4 in CADS, which is again back over in the South Silo. And then Tuesday and Thursday, 10 to 11 in drop-in and 1:30 to 2:30 in CADS, right? So kind of all over the place. I'm really, these are posted here so that I can look at them and know where I'm supposed to go on each day. Because usually my office hours are in the same place and same time. They're the same times, but they're in different places. So I have to remember where to go. But you can always look here, or you can look at my website. And they are right there. So easy enough. Here's my cat. Okay. So mathy things. Whoops, that's not what I meant to do. There we go. So I guess we should talk about antiderivatives. Where's the pen? So as the name might suggest, you're undoing a derivative. Or as I would rather think of it, we're finding the function that if I take its derivative, I get the thing I'm taking the antiderivative of. For example, if our function is, say, x to the fourth, I want to find a function whose derivative is x to the fourth. Yes. Can I zoom in more? Yes, I can. Okay. So, well, we know that when we take a derivative of a power function of x, it reduces the power by 1, right? The derivative is like you bring the power down, and then the new power is 1 less. So the antiderivative is going to force us to go the other way. It's going to be something like x to the fifth. That's not quite right. Because if we took the derivative of x to the fifth, we would get 5 times x to the fourth. We're off by a multiple of 5 meaning we have to divide by 5 or multiply by 1/5. And we also need to slap on a plus c, because when we differentiate, right, our answer could have been 1/5 x to the 5th plus 2, or 1/5 x to the 5th plus 7, 1/5 x to the 5th plus pi, or any plus constant, because the derivative of a constant is going to be 0. I should say the derivative of a constant on its own is going to be 0. Right? That 1/5, it's a constant. Its derivative isn't 0 because it's multiplied by a function of x. So as I often say, constant multiples hang out. Constants on their own, their derivative is 0. And it's pretty standard notation before we use the integral notation to use a lowercase f or whatever letter we're using for the function and an uppercase letter to represent the antiderivative of that function. So it's pretty understood that when I say f of x is x to the 4th, capital F of x is the antiderivative of little f of x. We'll probably not use that notation very long. So more generally, we have an anti-power rule. So just like the derivative of x to a power was that power times x to the power minus 1, the antiderivative of x to some power is going to be capital F of x equal to x to that power plus 1 divided by that new power. And then what's a constant? So you all should try this one. I want you to find the antiderivative for f of x equal to, what do I got here? X to the 7th, x to the 7th, plus x to the 1/3, plus x to the -6, plus 5. Give that a try. Here's what I'm thinking. I'm just going to throw this rule at each one of these because each of these are just, well, except for the last part, each of these are x to a power. Technically, the last part is 2, I guess, but well, we'll see. So x to the 7th, I'm going to add 1 to 7 and then divide by that new value. Same deal here. I'm going to get x to the 1/3 plus 1 is 4/3 divided by 4/3. Same deal here. -6 plus 1 is -5 divided by -5. And if you wanted to, although I never would, but you could think of this as 5 times x to the 0th power. It's unnecessary, but you could think of it that way. And then the antiderivative is going to be 5 times x to the 1st divided by 1, or just 5x. Which makes sense because the derivative of 5x is just 5. So the antiderivative of 5 is just 5x. And then, of course, let's see. The only thing I don't like about this answer, there's maybe 2 things I don't like. I don't love dividing by 4/3. I would definitely want to rewrite that as multiplying by 3/4. So if I was writing this answer in a more simplified way, I'd write it as x to the 8th over 8 plus 3/4 times x to the 4/3 minus x to the -5 over 5 plus 5x plus c. It's debatable as to how much you want to simplify this or what way feels more simplified, but that's totally fine. Couple other things to address here. Also, if I get off screen, please let me know. Let's see. So let's just, this notation is fine. It's cumbersome. So we're going to introduce the integral notation. For now, we're just going to say this just means find the antiderivative. So when I write this, say the integral of 5x to the 6 dx, for now, we're just going to say this means find the antiderivative of 5x to the 6th. I'm kind of going to ignore the 5, right? Constant multiples just hang out. In fact, if you want, well, no, we shouldn't do that yet. So this is going to be 5 times the antiderivative of x to the 6th is x to the 7th over 7. And then plus c. In a similar way, there's something I meant to say back here that I kind of got past. So back here for just 1 second, this anti-power rule is all well and good with one exception. There's a value of p that is not going to work for us. Specifically, if we're dividing by p plus 1, p better not be -1. Otherwise, you're going to divide by 0. So the antiderivative of x to the negative first, or 1 over x, doesn't adhere to the anti-power rule, but every other power of x does. So you all could find, maybe say, the antiderivative of 4 times cosine of x. You guys are probably done. So again, 4 just hangs out. The antiderivative of cosine is sine, because the derivative of sine is cosine, right? That should always be, like, when you're finding an antiderivative, you can always end that sentence with, because the derivative of the thing I just found is the thing I started with. That should always be the case. Whatever our answer is over here, if you took the derivative of this, you should get back to there. Or in other words, antiderivatives and derivatives should undo each other. If you did an antiderivative then a derivative, you should end up back at the same function you started with. There might be some rare, weird exceptions to that, but generally that is true. And the rare exceptions are just like domain issues that aren't really big deal. Let's look at a few more examples. Let's say we had, the integral, the antiderivative is the word I should be using, of 3 over 7x squared plus 6 divided by the cube root of x plus 9 divided by cosine squared of x. Bless you. Bless you again. Well, that looks terrible. And it is terrible. We definitely should simplify this expression before we try to anti-differentiate it. And that's a generally good rule of thumb, is if you can simplify something into just having x to a power or as some recognizable derivative of a function we already know, then that's definitely worthwhile. So I would certainly like to rewrite this as the antiderivative of 3/7 times x to the negative second plus 6 times x to the negative 1/3 plus 9 times, dividing by cosine is the same as multiplying by secant, or 1 over cosine of x is secant of x. So 1 over cosine squared of x is secant squared of x, a function that we recognize as a derivative of a known thing. So then we can anti-differentiate to our heart's content. We're going to get 3/7 times the antiderivative of x to the negative 2 is x to the negative 1 divided by negative 1 plus 6 times x to the negative 1/3. So negative 1/3. I need to add 1 to that. So since I made a mistake here, or not really, I didn't fix it, I'm just going to say plus 1. Right? I'm adding 1 to the power. And then I'm going to divide by that same power. Negative 1/3 plus 1 is positive 2/3. And then the 9 hangs out. And what's the antiderivative of secant squared? Or better, what function can we take the derivative of and get secant squared of x? Everybody should say tangent of x. I can't emphasize enough how important it is that you recognize that the reason the antiderivative of secant squared of x is tangent of x is because the derivative of tangent of x is equal to secant squared of x. That's like the whole game right there. That's a lot of what this is really about, is just knowing that an antiderivative of something, you just make sure it's the right thing by taking its derivative and seeing that you get back to where you started. Plus c. And then, yeah, I can't not simplify this. This is negative 3/7 times x to the negative first. 6 divided by 2/3 is 6 multiplied by 3/2, which is 9. X to the positive 2/3 plus 9 tangent of x plus c. Not super important, but a little important. Let's look at another example. We're about to get more interesting here, I promise. So I keep looking up there when the screen is literally right there. Problem is the screen doesn't always work, so I've gotten used to looking up there, and I should just look at the screen there. Let's look at, sure, this one's unexciting, fine. So we want to find the antiderivative of x to the fourth times x cubed plus 2x. So I should be extra clear. We cannot antidifferentiate things separately, meaning it is definitely not equal to the antiderivative of x to the fourth times the antiderivative of x cubed plus the antiderivative of 2x. Definitely not. More generally, I should note that the antiderivative of a function times another function is not equal to the antiderivative of the first thing times the antiderivative of the second thing. Very, very untrue. Or I should say, this is very true, that they're not equal. They're, no, almost never. Instead, we should simplify, right? We should definitely just say, oh yeah, we can multiply this out. X to the fourth times x cubed is x to the seventh. X to the fourth times 2x is 2x to the fifth. And then we can find the antiderivative in the usual way. We get x to the eighth over 8 plus 2x to the sixth over 6 plus c. And yeah, you could simplify that further. Look at one more relatively straightforward thing. The antiderivative of the fourth root of x cubed plus 3x to the fifth plus 2x all divided by x squared. And we definitely, so unlike kind of derivatives, I'm going to say something that's kind of not true, but fine. There really isn't a product rule for antiderivatives. It's kind of not true, but just believe me for now. There isn't really a product rule for antiderivatives. There isn't a quotient rule for antiderivatives. We have other methods of finding antiderivatives, which is what all of chapter 8 is really about, is all the methods of integration to be able to find the antiderivative of all kinds of functions. For now, we're kind of limited into really just finding antiderivatives of things we recognize as the derivative of a known thing. Here, we have to simplify this, right? And really, that's kind of the name of the game right now, is can we simplify it? Great, simplify it. So here, we're going to rewrite this as, first of all, each thing gets divided by x squared. So this is x to the 3/4 divided by x squared plus 3x to the fifth divided by x squared plus 2x divided by x squared. And then we're going to simplify each thing, hopefully to be written as x to a power. Not 1 over x to a power, but x to a power, whether that power is positive or negative. So we subtract the powers. The 3/4 minus 2 is 3/4 minus 8/4, which is negative 5/4. And then 5 minus 2 is 3, so we get 3x cubed. And then 1 minus 2 is negative 1, so we get 2x to the negative 1. And personally, I would rather think of this as 1 over x. Because I know a function, and you know a function, whose derivative is equal to 1 over x, the natural log of x. Unfortunately, that's not quite the right answer. Here's what it is. So we're going to get x to the, let's see, negative 5/4 plus 1 is negative 1/4. Dividing by a fraction is all the same as multiplying by its reciprocal. So instead of dividing by negative 1/4, we're going to multiply by negative 4 over 1, or just negative 4. We're going to get 3x to the 4th divided by 4. And we're going to get 2 times the natural log of the absolute value of x. There's a reason for this, which we'll get into later. The reason really is when you take a derivative, it's okay for the domain to get smaller. Here's an example. The derivative of the square root of x. The domain of this function is all non-negative numbers, right? X can be 0 and anything positive. If we take the derivative, we get 1 over 2 root x, whose domain is almost the same, but slightly smaller. Because this derivative, x can't be 0 here. So this function, the domain is everything from 0 to infinity inclusive of 0. And this derivative, its domain is a little bit smaller. So here's what I'm trying to say. When you take a derivative, it's okay for the domain to get smaller. When you take an antiderivative, it's okay for the domain to get larger, but not smaller. So the problem here is that 1 over x has a pretty big domain. X can be anything that's not 0. Natural log of x has a much lesser domain. X has to be positive for a natural log function, which is why we need the absolute values there, so that now x can be either positive or negative. So the domain didn't get smaller when we anti-differentiated. There's more to it, but that's a very short explanation as why we need that. We'll talk about it more at a later date, I promise. But for now, you should just know when you anti-differentiate 1 over x, you don't just get natural log of x, you get natural log of the absolute value of x. Okay. We end at what? 4:30? Yeah, 4:30. Okay, cool. So, plenty of time. Any function you know the derivative of, you know the antiderivative of its derivative. I know it seems like kind of an obvious statement, but let me just point out. We know lots of derivatives. We know the derivative of sine of x is cosine of x. We know the derivative of cosine of x is negative sine of x. We know the derivative of tangent of x is secant squared of x. We know the derivative of cotangent of x is negative cosecant squared of x. We know the derivative of secant of x is secant of x times tangent of x. We know the derivative of cosecant of x is negative cosecant of x times cotangent of x. The list goes on. We know what else? We know the derivative of e to the x is e to the x. We know the derivative of the natural log of x is 1 over x. We know the derivative of x to a power is that power times x to the power minus 1. What am I missing? Different base. We know the derivative of 2 to the x is 2 to the x times natural log of 2. We know the derivative of, I'm just using 2, right? It could be any base, really, right? It could be b to the x is b to the x times natural log of b. And the derivative of log base 2 of x is 1 over x natural log of 2. There's one other class of functions we're forgetting about, or I'm forgetting about. I think the square roots are caught up right here, right? Because the square root is what power? The 1/2 power. Yeah, thank you. The arc functions or the inverse trig functions. So we know the derivative of arc sine of x is 1 over the square root of 1 minus x squared. We know the derivative of arc tangent of x is 1 over 1 plus x squared. And arc secant. The derivative of arc secant of x is, we'll just go with the safe choice, 1 over x squared of x squared minus 1. So that means anything on the right-hand side, we know the antiderivative of. So I know the antiderivative cosine is sine. I know the antiderivative of negative sine is positive cosine, or the antiderivative of positive sine is negative cosine. Because you can always multiply both sides by whatever constant you want to. Similarly, the antiderivative of cosecant of x times cotangent of x is negative cosecant of x plus c. So anything on the right-hand side, its antiderivative is the function on the left-hand side of this derivative equation. It's good news. You already know a lot of antiderivatives. We're going to learn a lot more of that. So where I can see your teachers are leading you is that, and also I should point out that list of functions is also in Canvas much more nicely typed out. So if you want to it's like the list of derivatives / integrals to know, you can definitely take a look at that and be like, oh yeah, I know those ones already. But you definitely do want to make sure you know them in your heart and in your mind, I guess. So here's where things get more complicated. We know that for, say, f of x equal to e to the 4x plus sine of 3x plus the natural log of x squared plus 1, that the derivative is e to the 4x times 4 plus cosine of 3x times 3 plus 1 over x squared plus 1 times 2x. So when we integrate things, we antidifferentiate things, we have to be thoughtful about the chain rule. So for example, if we were finding the antiderivative of all this, of 4e to the 4x plus 3 cosine of 3x plus 2x over x squared plus 1. So here's how I'm actually thinking about this. I'm not thinking I just did all this. I'm pretending like that's not there. I'm thinking, well, cool. The 4 is going to hang out. And the antiderivative of e to the 4x, well, if we differentiate e to the 4x, we end up multiplying by 4 because of the chain rule. So when we antidifferentiate e to the 4x, we have to divide by 4 so that it accounts for the eventual multiplication by 4 that would happen if we took the derivative. So we're going to get e to the 4x divided by 4. In the same way, the antiderivative of cosine of 3x, well, the antiderivative of cosine of x is sine of x. The antiderivative of cosine of 3x is sine of 3x, but then we need to divide by 3. And here, this one I feel like is less obvious, but if you see something that's the derivative of the bottom on top, we can say, oh, that's going to be the natural log of the bottom. Because when you take the derivative of the natural log of some stuff, that stuff ends up in the denominator, and then we end up multiplying by the derivative of that stuff in the numerator. You might notice I didn't write absolute values. You might not notice, I don't know. The reason I didn't write them there is because x squared plus 1 is already always positive. So you don't need them there. Although it would be totally fine if we wrote them. And then we would simplify, and we would just get, obviously, e to the 4x plus sine of 3x plus the natural log of x squared plus 1. Let's see. Not surprisingly, right? That's the function we started with that we were taking the derivative of. But that kind of informs us as to, oh, if we look at this function and we would have ended up multiplying by a constant when we take the derivative, that means we have to divide by that constant when we take the antiderivative. It is kind of a shortcut of a process known as U substitution, which we kind of like to not do the long way. So let's look at another example. Let's say I lost my numbering here. Try to keep track of the numbering sometimes. 5. That's the wrong way, James. 6. Sure. We'll call this number 7. So for example, we could ask the question like, What's the antiderivative of e to the negative 9x plus sine of 6x plus 1 over 3x minus 2? So here's what I'm thinking about. I'm thinking that if I took the derivative of e to the negative 9x, I would get e to the negative 9x times negative 9. So the antiderivative is going to be e to the negative 9x divided by negative 9. Or I actually prefer to write as multiplied by negative 1/9. Because we can see that if we take the derivative of this, we're going to get negative 1/9 times e to the negative 9x times negative 9. And the negative 1/9 and the negative 9 are going to multiply to 1. And we're just going to get e to the negative 9x as desired. Similar deal here. The antiderivative of sine is negative cosine. Sine and cosine always feels like a switch, kind of. But derivatives of sine, we know the derivative of sine and cosine. Derivative of sine is cosine. Derivative of cosine is negative sine. The antiderivatives, you switch the signs. So the antiderivative of cosine is positive sine. The antiderivative of sine is negative cosine. So we're going to get negative cosine of 6x times what? Almost. Times 1/6 divided by divided by 6. Oh my goodness. Right, if we were finding the derivative, it would be 6 times cosine of 6x. But we're finding the antiderivative. Yeah. So let me finish this question and we'll see why. So here, same deal. The antiderivative here is going to be the natural log of the absolute value of 3x minus 2, but not quite. Because if you took the derivative of this natural log of this stuff and used the chain rule, the derivative would be 1 over the stuff multiplied by the derivative of the stuff, which is 3. But that's not what I have here. I don't have 1 over 3x minus 2 times 3. I don't have the times 3. So I have to divide by 3 or multiply by 1/3 to account for that. So this is our answer. Let's see why it's our answer. Let's take the derivative of it. So I guess I'll call this capital F of x. And now if we take the derivative, look what happens. So here's our derivative. The negative 1/9 hangs out. The derivative of e to the stuff is e to the stuff times the derivative of the stuff, and the derivative of negative 9x is negative 9. Minus 1/6 hangs out. The derivative of cosine of some stuff is negative sine of the stuff multiplied by the derivative of the inside stuff, and the derivative of 6x is 6. Similar deal here. The 1/3 constant multiple hangs out in front. The derivative of the natural log of some stuff is 1 over the stuff multiplied by the derivative of that stuff, and the derivative of 3x minus 2 is 3. The derivative of c is 0. Hey, look, that's exactly, let's see, those cancel. You get e to the negative 9x. The negative 1/6 and the 6, or the 1/6 and 6 cancel, and the negative becomes a positive sine of 6x. And the 1/3 and the 3 multiply to 1, and you get 1 over 3x minus 2. Exactly the function we started with antidifferentiating. So we found the antiderivative of this. It was equal to that, and we checked, and it's true because the derivative of this gets you back to where you started. So antidifferentiation and differentiation, if you do them in succession, should always get you back to the function you started with, which is why we need the negative 1/9 out in front here. Otherwise, our derivative wouldn't be correct, which is why we need the negative 1/6 out in front here, which is why we need the 1/3 out in front here. Because each of these functions we multiply by not negative 9 or 6 or positive 3 when we differentiate. Yes, which is why you need to be really good at differentiation. So when you check your work, you're checking it correctly. But yeah, that is exactly true. If you're ever finding an antiderivative and you're not sure, you can check to see, well, if I take the derivative of my answer, is it what I'm expecting to get? In fact, that brings up an excellent question. Sometimes people like to ask, we're not quite there yet, but here. What is the plus C for? So the plus C is the fact that There's lots of correct answers, unfortunately. Let me actually write a simpler example. So if I wanted to find, say, the numbers, James, numbers, sure. If I wanted to find, say, the antiderivative of secant of 4x times tangent of 4x, well, I know the, whoops, sorry. I know the antiderivative of secant of x times tangent of x is secant of x, because the derivative of secant of x is secant of x times tangent of x. So here, I'm thinking the answer should be something like secant of 4x. But the problem with this answer is, what's the derivative? What's the derivative of secant of 4x? Right, it's secant of 4x times tangent of 4x times the derivative of 4x, which is 4. Oh, that's not the same as that. My answer is not right. But it's always easy to fix being off by a constant multiple. You just multiply by the reciprocal. So if I'm off by a multiple of 4, I'm going to multiply by 1/4. So that then the 1/4 and the 4 multiply, and things work out nicely. Now, to answer your question about the plus c, my answer could have been plus 7. Or it could have been 1/4 secant of 4x plus -20. And I could go on, right? Literally any constant could be out there, because what's the derivative of 7? What's the derivative of -20? Right? Any constant could go over there, so that we don't have to kind of spend time explaining ourselves that, yes, any constant goes. We just say it's plus c. It's plus whatever constant we want it to be. Now, that actually brings up kind of an interesting question is, sometimes we like to be more specific about what the actual function is. So we might say something like, example here, 1 second. Come back to you. There we go. I don't love, that's not the one I wanted. That's not the one I wanted either. There we go. That's true. When I say something like our function f of x is equal to 2e to the 3t plus, sorry, e to the 3x plus 2x. And then also give an initial condition that f of 0 is equal to, say, 1. Sorry, I made one tiny mistake. It's fixable though. Apologies. The derivative, f prime of x, is equal to 2e to the 3x plus 2x, and f of 0 is equal to 1. And the question here is, we want to find f of x, the antiderivative of f prime of x. I'll say that again, right? F of x, little f of x, is the antiderivative of its derivative. Seems reasonable. Okay, so we're going to antidifferentiate. So we're going to get f of x equal to, so let's see, the antiderivative of 2e to the 3x is going to be 2e to the 3x, and then I need to divide by what? 3. Because my derivative would make me multiply by 3. And the antiderivative of 2x is going to be 2x squared over 2, or just x squared. And then a plus c. And normally, that would be our general antiderivative. Like, cool, whatever the antiderivative is, it's something like that. But they've also told us something about what the actual function is. They told us, hey, if I plug in 0, the value of the function should be 1. Meaning, really what this means is, when you're given an initial condition like this, where they tell you the value of your function at some input, what that means is find the value of c. That's what the question is actually saying when they give you an initial condition is, I have given you enough information to find that constant's actual value for this particular situation. So let's do it. We're going to plug in 0 for x. It's going to be 2/3 e to the 3 times 0 plus 0 squared plus c, and it should equal 1. And then we can solve for c. So e to the 0 is 1. So I have 2/3 plus c is equal to 1. So c is equal to 1 minus 2/3, which is 1/3. And I would point out that technically we haven't finished the question. We've given all the information, but we haven't put it all together. the question asks us to find f of x. So we need to go back and say, great, our actual answer, f of x, is going to be 2/3 e to the 3x plus x squared plus 1/3. That's one example of an initial condition problem or an initial value problem, where you're finding the function and you're finding not the general solution, you're finding the particular solution. Let's look at a couple more examples. Sure. So I want to find the antiderivative of, oh, sure, 1 over x squared plus 1 plus 7 to the x. The first half of this, I think everyone probably knows. The antiderivative of 1 over x squared plus 1 is one of those arc functions. Specifically, it's arctangent. You know how I know it's arctangent? Because tangent starts with t, and the plus sign looks like a t. I know it's dumb, but it works. The other ones have a minus sign, right? The derivative of arc sine is 1 over square root of 1 minus x squared, and the derivative of arc secant is 1 over x squared of x squared minus 1. The only one that has a plus, which looks like the letter t, is arctangent. Easy. Kind of. So we know we're going to get arctangent of x, or inverse tangent if you prefer to write it that way, plus, the antiderivative of 7 to the x. Well, what's the derivative of 7 to the x? It's 7 to the x times a constant. Natural log of 7. So I'll say it again. This one's a slightly it's not really actually different. It's not, no. If taking the derivative of a function makes you multiply by a constant, and I want to emphasize the constant part there, then the antiderivative is going to make you divide by that same constant. No caveats. Always true. I think. Pretty sure it's always true. So the antiderivative of 7 to the x is going to be 7 to the x divided by the natural log of 7, or multiplied by 1 over the natural log of 7. Because if we took the derivative of this, the 1 over natural log of 7 is going to hang out, and the derivative of 7 to the x is going to be exactly that, and the natural log of 7s are going to cancel out. Or divide to 1, if you prefer to say it that way. Yeah. No, I can put it on top. Well, I can say I can put it on top or in front or, yeah. But no, it doesn't, order of multiplication doesn't matter. Yeah. Yeah, I don't know why. I guess I prefer to put the constant multiple in front typically. Even though 1 over natural log of 7 is kind of funky, it still qualifies as a constant multiple. And in my mind, we usually put constant multiples in front of functions. I don't know why, but we do. We almost always do. There was something else that I wanted to say. Sure. It went away. Oh, let's do that one. Sure. So I was going to grab one of these. So these look fun. Oh, yeah. So let's say our function is this. Yeah. That looks gross. Sure. Let's try this one. Sorry, I keep waffling back and forth between which one of these. Yeah, sure, we'll do that one. Fine. F of x is 2 to the x plus x to the third, and we know that the antiderivative capital F evaluated at 0 is equal to 0. Find capital F of x. Okay, go for it. Find the antiderivative. No, so I use different labeling here. This is my function, and capital F is the antiderivative. And you got to find C as well. Your C value should be kind of gross. But not too terrible. We should do one of those. There's our general antiderivative, 2 to the x divided by natural log of 2, or if you prefer, 1 over natural log of 2 times 2 to the x, it's the same thing, plus x to the fourth over 4 plus a constant. And now we're going to plug in our initial conditions. The fact that when x is equal to 0, the whole thing is equal to 0. So I'm plugging in 0 for x. So I have 2 to the 0 over natural log of 2 plus 0 to the fourth over 4, which feels silly to write, plus c equal to f of 0, which is 0. I don't really need to write f of 0. We know that f of 0 is equal to 0. Just like over in the previous one we did up here, we didn't really have to write f of 0 here. We just could have written 1 because f of 0 was equal to 1. Okay. 0 to the fourth is 0. What's 2 to the 0th? 1. So we got 0 equal to 1 over natural log of 2 plus c. So subtracting 1 over natural log of 2 from both sides, we get negative 1 over natural log of 2 is equal to c. And then our final answer is that the antiderivative capital F of x is equal to 2 to the x over natural log of 2 plus x to the fourth over 4 minus 1 over natural log of 2. A little gnarly, but not too terrible. So some interesting questions to ask. Here's a question I have often asked on an exam when I used to teach this class for actual credit. When I used to give exams, not here, somewhere else. True or false? The antiderivative of 2x times cosine of x is equal to x squared times sine of x plus c. They want you to think it's true. How would you check? I don't know how to find, we don't currently know how to find the antiderivative of 2x times cosine of x. We will learn how to eventually. Well, the way we've talked about checking the whole time, if the antiderivative of this is supposed to equal that, then the derivative of that should equal this. Let's check. What's the derivative of x squared multiplied by sine of x? Well, I said the word multiplied. Probably means I have to use the product rule. And I do. The derivative here is going to be 2x times sine of x plus x squared times cosine of x. I didn't write the plus c over here because we knew the derivative of plus c was going to be 0. That is definitely not 2x times cosine of x. So false in a big way. I wouldn't be surprised if someone asked a question like this on an exam. It seems it's a good question that tests your knowledge of what an antiderivative actually is. How about this other one here? That was probably number 12, I think. Sure, 13. Another true false. Sure, let's do that one. The antiderivative of the arctangent function divided by x squared is equal to the natural log of x minus 1/2 the natural log of 1 plus x squared minus the arctangent or inverse tangent of x divided by x plus c. So intuition says that looks really complicated. It's probably right? They probably didn't give us something that looked easy that was wrong. Instead, it probably looks complicated because that's how complicated it actually is. Let's find out. So same process. We're going to take the derivative of this side and see if we get the stuff we were supposed to be anti-differentiating. We will learn how to anti-differentiate this eventually. But we're going to start off by finding the derivative of all that jazz over there. The natural log of x minus 1/2 the natural log of 1 plus x squared minus the inverse tangent of x divided by x. I don't need the plus c. We know its derivative is going to be 0. Let's see what we get. Derivative of the natural log of x is 1 over x. The 1/2 hangs out. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, which is 2x, minus, okay, quotient rule over here. It's the bottom times the derivative of the top, which is 1 over 1 plus x squared, minus the top times the derivative of the bottom, which is 1, all divided by the bottom squared. Well, that looks terrible. I guess we have to simplify it. That's really terrible. Yeah, I don't love it. See, what did I do before? Okay, sure, that's better. Yeah. So here's what we're going to do. We're going to write this as 1 over x. The 2 here and the 2 here cancel. We can write this as minus x over 1 plus x squared. And then what I'm going to do is I'm going to take this x squared out in front as 1 over x squared, multiply by, here I have x over 1 plus x squared, and here I have the inverse tangent of x. I'm running out of room. Sure. Looking bad, right? This doesn't look good. This is terrible. But we continue on. So let's see. We've got 1 over x minus x over 1 plus x squared. Distributing this, we have a 1 over x squared times x over that. One of the x's will cancel, and we'll get a 1 over x times 1 plus x squared. And then we have a plus, because it's a minus times a minus, inverse tangent of x divided by x squared. Well, I see hope, right? I started with the inverse tangent of x over x squared. That's what I'm trying to get to, right? I'm hoping the derivative of all this is equal to that. So that's the piece I want. I need all this to go away. And I know that looks like a minus 1 over x. No, it's a positive 1 over x. So let's see here. I think I need a common denominator. If I multiply this positive 1, over x by 1 plus x squared over 1 plus x squared, and this minus x over 1 plus x squared times an x over x, and finally, this is just what it is, plus the thing I'm hoping sticks around. Let's see here. So simplifying this, this is one big fraction. It's going to be 1 plus x squared minus x squared minus 1 all over the same common denominator. Oh, look, all those things get to cancel out. That's 1 minus 1, x squared minus x squared. That's a big old 0. So after quite a bit of work, we see that it's true. The antiderivative of the inverse tangent of x over x squared is indeed equal to this gross function over here. And the way we checked, oh, sorry, you can't see where I'm pointing. No, yeah, sorry, I'm pointing too high. The antiderivative of inverse tangent of x over x squared is indeed equal to the natural log of x minus 1/2 natural log of 1 plus x squared minus inverse tangent of x over x plus c. Because the derivative of all that is in fact equal to that. I can't say it enough times. right? The antiderivative of something is equal to something because the derivative of that something is equal to the thing you started with. If there's anything you've heard me say today, that is the one thing you should remember is antiderivatives and derivatives undo each other. In fact, spraying water. Sometimes people draw a little picture that's not super helpful, but I'm gonna draw it anyway. So if you have like f of x here and it's antiderivative over here, to get from f of x to capital F of x, you anti-differentiate. To get from f of x to little f of x, you differentiate. The circle of not life, math. The one thing I'll say here is that yes, these things undo each other. You always get back to where you started, kind of. But if you start here and then you differentiate and anti-differentiate, technically you get to a different place because when you anti-differentiate, you're throwing on a plus c, and the constant you're adding could be a different constant than it was before. So sometimes antiderivatives differ by a constant. That's totally fine. It happens sometimes. Sometimes you might anti-differentiate a function and get a slightly different answer than someone else because you used a different method of integration. And sometimes the methods can make it look like the answers are a little bit different, but they're not. They just happen to differ by a constant, which we really aren't differing at all. Let's see. Can I say anything useful in 3 minutes? Maybe. Not all that, though. So that's enough. I could say more. I think that feels like a welcome stopping place, though. I would say on Thursday, we will start talking about area under a curve and estimating the area under a curve. Okay, that's definitely, so we talked about anti-differentiation. That's going to stick around. And then we're going to talk about finding the area under a curve. And eventually we're going to circle back to, oh yeah, kind of like with with the limit definition of the derivative, how we did it the long way first. And then we learned a bunch of shortcuts like the power rule and the product rule and the quotient rule and the chain rule. In a similar way, there's kind of a long route to find the area under a curve. And then we're going to see that there's a much shorter way of doing it using antiderivatives. That's where we're going. Which is why it's important to be able to anti-differentiate functions so that we can find the area under the curve the fast way versus doing it the longest way ever.